Namaste and welcome back to this lecture on mathematical foundations for machine learning. In the last couple of lectures we have been looking at the idea of optimization, and we looked at matrix derivatives and all. In today's lecture what we will be doing is we will just recap the ideas of matrix derivatives once, and then we will look at the idea of linear regression through ordinary least squares. We just look at least squares and linear regression, and what we will do is we will look at it from the perspective of the matrix calculus, and then we will follow it up with the ideas of principal component analysis using Lagrangian multiplication, using Lagrangian multiplier. Okay. So, let us look at our what do you call our least squares solution. So, what was that? We basically have this. So, before that we just do a quick recap of our matrix derivatives, recap of matrix derivatives. So, what we are going to do is we will quickly list out some of the derivatives that we have had. So, basically what we are going to do is we are looking at f, which is going to map from, let us say, Rn to R, right. What does that mean? The function, if you are going to have y is equal to, let us say, f of x, this x is going to be an element of Rn, is going to be, okay, I will say f of x, where x is the x vector is basically x1, x2, etc., xn, right. Now, what we do is we will quickly have our ideas of, bring back the ideas of gradient and stuff. So, we have the gradient of f, which we called as grad f. So, I will say gradient of f is nothing but f of this x vector that I have, which is nothing but dou f of that x vector divided by dou x vector, which is going to be I mean, you can take it as dou let us say dou f by dou x1, dou f by dou x2, etc., dou f by dou xn is what we have. And we also studied some properties of matrix derivatives. The first one we said that we will just do this. One, we have, let us say I have a function which is nothing but y is equal to x transpose b, which means you are going to have this is going to be of the form, let us say x1, x2, etc., xn into, let us say, b1, b2, etc., bn. Now, what we are going to get? I am going to have y is equal to x1 b1 plus x2 b2 plus etc. xn bn. So, what I am going to do is I am going to look at dou y by, let us say, dou x vector, which is going to give me, let us say, b1 b2 etc. bn, which is nothing but b transpose. I mean, we also write this as b transpose x. So, which is basically b transpose, and so this is something which we have. And I mean, if you want to put that in the other layout where you want to put it as a column vector, you can write this as a b vector, like, you know, right, you can do that. If you arrange your gradient as a column vector, if grad f is taken as a column vector, then we have dou y by dou x vector is nothing but b vector itself, right. This is b transpose, right. So, this is what we have, and we have also studied the derivative of dou by dou x vector of x transpose a x, which we said this is going to be a transpose plus a into the vector x, and if a were symmetric, if a is symmetric, then we are going to have this. Then we have the derivative of our x transpose Ax with respect to that x vector is nothing but 2 Ax vector. This is what we have, right, and these are all things which are clear to us. This is fine. Now what we are going to do is we are going to approach this least squares problem from this perspective. So what we have let's take in our format where we have b vector is equal to say a x vector, right, and we have d is an element of Rm, and A is basically an m by n real matrix and x is basically an element of Rn. This is what we have, right. We will probably take a simple example and then we will figure out like what it is, and we will be able to get much better understanding. So then we will generalize this result. So what we are going to do is I am going to take, let us say, b1, b2, b3. Remember we had this vector valued functions and stuff. So we have b1 is equal to, let me say, and I take x1 x2. So in this case b is going to be element of R3, then A is basically a 3 by 2 matrix and x is basically an element of R2. This is what we have. So I have A11 x1 plus A12 x2, then A21 x1 plus A22 x2, then A31 x1 plus A32 x2. This is what we have, and we know that so the functions are basically going to be b1 is equal to A11 x1 plus A12 x2 and b2 is equal to A21 x1 plus A22 x2 and b3 is equal to A31 x1 plus A32 x2, right. This is what we have. Now the point is you are expected to solve for this x1 and x2, and we do not have an x1 and x2 which would actually give B, this set of b1, b2, b3. Let us assume that B does not belong to the column space of A, implies there exists no x1 x2, there exists no x1 comma x2 such that Ax is equal to B. Therefore we opt for a least squared solution, which means I may not get b1, b2, b3, but I may get something else, which implies I may get b1 hat, b2 hat and b3 hat, which is equal to, I will put this as A11, let us say x1 star plus A12 x2 star, then A21 x1 star plus A22 x2 star, A31 x1 star plus A32 x2 star. This is what we have. This would work because B I will call this as B hat, which is basically my B1, B2, B3 hat, put all these things, and this is not equal to B vector. This is not equal to B vector because you are trying to approximate this B vector in the column space of A, which is given by my B hat, right. So therefore there is an error that exists. So what is that? Error is equal to, you have this error vector which is nothing but B minus B hat. Therefore I want this error squared to be minimum, squared error to be minimum. So what I will do is I will basically look at this error squared is nothing but I have the length of B minus B hat, this whole squared, this has to be minimized, this has to be minimized, squared sense we have. So now what do we do? We know that this is going to be B minus B hat is nothing but, let us say I will take it as Ax, and then the optimal one I am going to equate, when I equate the gradient to be equal to 0, then I will get the optimal value of x. So I have this, right, I have this error squared to be minimum. So let me call this as E squared. Now what I do, error squared error, basically I will call it as E. Now what I want is I want basically dou E by dou x, dou E by dou x vector, right. What is dou E by dou x vector? We already know this. So we will call this as dou, okay, let me write this here. This is nothing but what do I have? I have this the length of this vector what is the vector we have? We have b minus a11 x1 minus a12 x2 or b1, b2 minus a21 x1 minus a22 x2, and then we have b3 minus a31 x1 minus a32 x2. This is the vector that I have, right. Now what I want is I want the squared length to be minimized. So what I will do is I will take the square. So this, let us write this E. So E is going to be b1 minus a11 x1 minus a12 x2 the whole square plus b2 minus a21 x1 minus a22 x2 the whole square plus b3 minus a31 x1 minus a32 x2 the whole square. This is what we have. Now what is this? I want to look at dou E by dou x, which is basically the partial derivative. So what am I going to get? I am going to get dou E by dou x1, dou E by dou x2 and dou E by dou x3. This is what I have, right. So what do we get here? We basically have this to be 2 into what do we have, b1 minus a11 x1. You can actually this is okay, this is the error that I have. So b11 minus a11 x1 minus a12 x2 the whole squared was there. So taking that derivative, this is gone. So let me do this. This is not even dou E by dou x. So now what I will do is I will take it this way. Let us forget about this. Let us approach this in a different way. So I have this. So I have b minus ax the whole square, which is nothing but, I will write this as b minus ax the whole transpose into b minus ax. This is what I have, right, because we know that if you take any vector, so the squared length of the vector is nothing but y transpose y. This is what we have. So we have b minus ax transpose into b minus ax. This is what we get, which is nothing but, let me write this as b transpose minus ax the whole transpose into b minus ax. This is what we have, right. Let me call this as squared error, or let me call this as E. So what is this? This is going to be b transpose b minus, I have b transpose ax minus ax the whole transpose b plus I have ax the whole transpose ax. This is what I have, right. This is what I have. Now I want to look at this dou E by dou x vector. If I do this, this is what I need to find out. But before that, let us pay a small let us pay some attention to this term. We have b transpose ax and the other term is ax the whole transpose b. This is what we have, right. And this is basically saying b transpose into x, that is saying ax transpose into b. So these two are basically the same. So what do we have? I have minus 2 b transpose ax, right, or minus 2 b 2 times, let me also write it this way. So what I will do is I will write this as b transpose into ax, I will write this as x transpose into a transpose b, right. This also becomes x transpose into a transpose b. So this is what I have. So what do we get finally? I get from here, I get to see my error vector E is going to be the following. E is going to be b transpose b minus 2 x transpose a transpose b plus x transpose a transpose a into x. This is what I have. Now what I need to do, I need to take the derivative of this with respect to the x vector, dou E by dou x vector. If I take this, this fellow is d void of this b transpose b is d void of x term. So, that becomes 0, then what do I have? Minus 2 x transpose into A transpose B, which is the same as minus 2 times. So, if you take the derivative of this, we just saw in the previous case where we had x transpose A transpose B, the derivative of x transpose B is nothing but the B vector itself. So, I am going to take it as minus 2 times A transpose B. Then I know that this is going to be a real symmetric matrix, let me call this as M. So, what I am going to get? I am going to get x transpose mx, and the derivative of x transpose mx is going to be m plus m transpose into x, but m plus m transpose is the same as 2m because m is symmetric. This is symmetric. This is symmetric. So, what we have? We have 2 times A transpose A to x, this is what we have. Now, we know that in order to find the optimal solution, we need to equate this gradient to be equal to 0. This is basically the gradient E. So, I am going to equate this gradient E to be equal to 0, which implies I have minus 2 A transpose B plus, okay, let me to find the optimal solution. To find the optimal x star, which is say x star, we equate del E equal to 0. So, I have 2 minus 2 A transpose B plus 2 times A transpose A x star is equal to 0, which implies I have A transpose A times x star is equal to A transpose B, and therefore, x star is equal to A transpose A the whole inverse A transpose B, and that is exactly what we saw in our least square solutions by the linear algebraic way, where we projected the vector B onto the column space of A and then tried to find a solution for that projection which is there in the column space of A. So, this we see that okay, the results are like what we had with the calculus and what we had in the linear algebraic way are both the same. So, this we did with the help of gradient of the error function, and we looked at even what you call, we looked at the matrix derivatives and so on, and we got to this result. Now, what we do is you see that this consistency. So, our learning is like in terms of linear algebra and in terms of calculus is right. Now, what we will do is we will go to the next one where I am going to talk about the idea of principal component analysis. Again, we are going to derive the optimal direction which would maximize my variance, right. So, I want to look at principal component analysis, basically deals with, or it is basically a dimensionality reduction technique where you try to project data onto the directions of maximum variance, that is what direction of the maximum variance. So, basically you are going to get a low dimension approximation or to the data that you have, right, low dimension approximation you are going to do. So, what we will do is we look at principal component analysis. Again, we are going to use Lagrange multiplier and so on. So, we are going to look at the notion of Lagrange multiplier and go ahead doing this. Okay. Okay, so what is it that we have in the first place? So, first of all, let us understand we are going to look at the covariance matrix. You already know that in case of PCA the direction of maximum variance corresponds to the eigenvector associated with the dominant eigenvalue of the I mean basically the eigenvector of the covariance matrix associated with the dominant eigenvalue. That is the first principal axis you had, and the second principal component is the second dominant eigenvalue, and you see that the principal components are basically orthogonal to each other, they are perpendicular to each other. You are basically looking for orthonormal basis for the for your covariance matrix, your column space of the covariance matrix, which is going to be your orthonormal eigenvectors, right. So, what is it that we are going to do? The first thing that we need to understand as far as the covariance matrix is concerned, as far as PCA is concerned, what is the goal? The objective is to find a low dimensional projection projection of the data points of the data points, let us say y in, let us say R, let me use R n. So, n data points I want to look at, right. I use y in R n, which is basically given by, say, some x is equal to W transpose into y minus b, right. We are going to have this where, which is going to such that the variance of x is variance of x is maximized. Right. And the constraint that we have here is you need to find out that direction in which the variance is maximized. That means you need to figure out that W, which is basically the unit vector in whose direction this variance is basically maximized. So, we have such that subject to the constraint W transpose W is equal to 1. Okay. So, basically what are we trying to do? We are trying to, you have a data vector and you basically try to project this data vector into some direction. You need to find that direction along which the variance is basically maximized, right, along which the variance is basically maximized. So, let us look at let us look at this, how do we go about doing this. Okay. Okay. So, first of all let us understand, let us get this, what is that. So, let us do this Lagrangian. So, I am going to call, let L be the Lagrangian formulation. So, let the Lagrangian formulation be L be L of, what I am going to do, I am going to take the W vector, I am going to take the B vector and I am going to also take the lambda. Lambda is basically the Lagrangian multiplier that we have. So, what is that? This is going to be the Lagrangian, which is given by L of W comma B comma lambda, right, which is equal to, let us say, 1 by n. I want to look at the variance. How do I compute the variance? From the statistical idea, we know that the variance is going to be the summation x I minus x bar the whole squared. You remember this summation. So, the variance is basically given by, if you recall, variance is nothing but expectation of x squared minus expectation of x the whole square, which is nothing but you have 1 by n times summation of, I have for every point x I minus 1 by n times sigma x I the whole square, right. You E of x, okay, let me rewrite this here. Okay, first of all, okay, let us do this. So, the variance of a set of data points is given by the variance of a set of data points is given by so, the variance of x is equal to, you have 1 by n sigma x I minus 1 by n sigma x I, this is going to be 1 by n into sigma of x I minus x bar the whole square, right. this is the variance. What is this? This is basically expected value of x minus x bar the whole square. If you recollect the expression for variance, it is going to be x minus e of x the whole square. This is what we have. X is here, e of x is here, the whole squared, average is going to be 1 by n, right. So, this is what we have. So, what is it? Now, what we are going to do is I am going to bring in all these ideas together and then formulate the Lagrangian, and then I am going to get the value of the unit vector, the direction and all those things. Okay. So, let us look at that. So, what do we have? I have the Lagrangian now to be Lagrangian of this w, b, and the lambda is nothing but 1 by n sigma. I will do this as xi minus 1 by n sigma xi the whole square, that is the variance of it, plus lambda into w transpose w minus 1. So, this is my Lagrangian formulation. I have the variance, this is the objective function which needs to be maximized, and the condition is this basically w transpose w is equal to 1. So, to maximize the variance, constraint is being this guy, w transpose w is equal to 1, right. So, that is the constraint. So, I will write it here. Let us take this to be the objective function, the cost function or the objective function, and this is going to be my constraint. This is what I have. So, let us express this whatever I have 1 by n into xi minus 1 by n into xi the whole squared and all those things. This is nothing but 1 by n summation over I, in this case everywhere it is going to be summation over I. So, what do I have? I have 1 by n summation over I. xi is nothing but we have already written, which is w transpose into yi minus b. So, this is over I. So, what do I have? I have w transpose into y minus b. Instead of y, it is going to be yi for every value of y. So, I have yi minus b minus 1 by n times minus 1 by n times, what do I have? Average of this values, this is over I, this is nothing but w transpose into, this is w transpose into yi minus b the whole squared. This is what I have, whole square, plus of course my constraint will still remain w transpose w minus 1, right. Okay. So, I can take this w transpose out. So, I have 1 by n into sigma over I will take w transpose everywhere. I will take this as yi minus b minus 1 by n times sigma yi minus b the whole squared, everything squared, right, plus lambda into w transpose w minus 1. This is what I have, right. Great. Now, let us look at what this is. This is nothing but 1 by n summation over I. I would still have this w transpose. Now, what is this yi minus b minus 1 by n into yi minus b the whole square, that is going to be, I am going to write this as w transpose into yi minus y bar the whole square, right, yi minus y bar the whole square. Actually, if you see, this is over I. So, I have this which is nothing but yi minus y bar the whole square plus lambda into w transpose lambda minus 1, right. So, this is nothing but w transpose into yi minus b minus you have 1 by n sigma yi, then minus 1 by n sigma b. Sigma b is going to be nb divided by n is going to be just b. So, this is going to be minus b, and that minus of minus b plus b gets knocked out. So, you just have 1 by n sigma yi, which is nothing but y bar, that is the mean vector that we have, mean. Now, what we have, let us write this. So, this is nothing but 1 by n sigma over I W transpose into, I will write this as, this is nothing but, if you look at this, if you look at this expression, this is, it says something A transpose B, it is basically the whole squared kind of you have, which is nothing but of the form, I will write it, just check this, this is going to be y I minus y bar, right, y I minus y bar into y I minus y bar the whole transpose into W. This is a kind of, we have this y W transpose into y I minus y bar into y I minus y transpose the whole bar into W. So, that is what we are going to have, plus lambda times W transpose W minus 1, right. So, this is what we have. So, let me rewrite this, this is going to be, which is equal to W transpose into 1 by n sigma over I have y I minus y bar the into y I minus y bar the whole transpose into W plus lambda into W transpose W minus 1. Now, if you look at this, if you look at this expression, this is basically your covariance matrix of y that you have, y I minus y bar into y I minus y bar the whole transpose summation, that is going to be the covariance matrix. So, where let us say y bar is equal to sigma I y I by n, this is what we have. So, this is going to be my Lagrangian. So, what I do is I will say dl by dw, this has to be, you have to find out the w vector. So, this has to be equated to 0. So, I will say dl by dw vector is going to give me 0. So, what is this? If I take this, this is of the form x transpose A x, then I have plus lambda into w transpose w minus 1. So, what am I going to get? I am going to have this, this is nothing but, this is of the form x transpose A x. So, what is that going to be? This is just going to be A x, the derivative of this with respect to w, this entire term with respect to w, this is of the form say x transpose A x. What is that going to give me? That is just going to give me, let us look at this. So, this is going to be 1 by n sigma y I, this is over I, y I minus y bar into y I minus y bar the whole transpose, x transpose A x, we know that this is going to be A plus A transpose into x, the derivative of that is going to be A plus A transpose into x. So, and this is going to be a symmetric matrix, always remember A into A transpose is a symmetric matrix, A transpose A is also a symmetric matrix. So, this is a symmetric matrix. So, I will get 2 by n here, I will get 2 by n into this into let us say W is equal to, there I have W transpose W. So, I will get 2 lambda W, 2 lambda W, this is what I am going to have, right. So, these 2 and that 2 will get knocked off. So, what do we have? I have 1 by n sigma I y I into minus y bar into y I minus y bar the whole transpose W is equal to lambda W, right. This is interesting. Now, if you look at this, this entire thing is a matrix. If you look at this entire thing is going to be a matrix of the form, let us say A W is equal to lambda W. Oh, now, what is that actually? A W is equal to lambda W, that is basically the equation of your eigenvector, the equation of the eigenvector, right. So, the equation of the eigenvector, right. Therefore, what do we see? If you want to find out that W which is going to maximize the which is going to minimize this or maximize the variance that you have. So, this W you are basically trying to maximize the variance. So, let me try this. This is basically maximizing the variance, right. So, you have maximizing the variance. So, what do we have here? This entire thing A W is equal to lambda W is the eigenvector equation, and you are trying to maximize the variance. So, what are we going to get? A W is equal to lambda W corresponds to eigenvector. Therefore, what we say is W must be the eigenvector of the covariance matrix, must be the eigenvector of the covariance matrix. In fact, this what we have here is the covariance matrix, covariance matrix of Y. In fact, what we see here, this is basically my covariance matrix, this entire stuff, right. This is going to be my yi, where is this 1 by n into, yeah, this guy is basically my covariance matrix. So, we have we figured out that, look, in order to maximize the variance, W must be the eigenvector of the covariance matrix. So, to maximize the variance, we must look at the direction, we must look at the eigenvector of the covariance matrix. But there is a problem here. What is the problem? You may have multiple eigen directions for different eigenvalues, you may have multiple, I mean, you may have different eigenvectors. So, among all the eigenvectors, which is the one that I need to choose? So, the question here is, question, if the covariance matrix is n by n, if the covariance matrix is an n by n matrix, n by n real symmetric matrix, there are at most n eigen directions. So, which one to choose? That is a question. Which one to choose? That is where the problem is, right. How do we get this? Which one to choose? So, that is where I need to find out the value of lambda, right. So, let us look at this. So, what is the value of L, the Lagrangian that we have? This whatever that we have had here, this expression that we have here, which is basically lambda W, this expression, let me call this as 1. So, let me write this 1 expression again. So, this 1 is nothing but 1 by n, you have sigma yi minus y bar into yi minus y bar, the whole transpose, the whole thing into W is equal to lambda W. This is what we had. So, what we will do is we will substitute this in our expression, in our the Lagrangian expression. So, L is equal to substituting this, substituting this in Lagrangian, we get L is equal to, what was that we had? what was L? W transpose lambda W. You remember this we had, what is the Lagrange equation? Let us do the Lagrangian again. So, we get L is equal to W transpose into 1 by n sigma y I minus y bar into y I minus y bar the whole transpose into W, this is what we had, plus lambda into W transpose W minus 1, this is what we had. Now, this expression is basically what is lambda W. So, what we will do is I will write L is equal to W transpose lambda W, right, and we have W transpose lambda W plus lambda into W transpose W minus 1 minus lambda, right, this is what we have. So, what is that basically? That tells you that L is equal to lambda. Why L is equal to lambda? Let us do, why should we L be equal to lambda? We see this, we were looking for, so let me write this here, L is equal to W transpose lambda W plus lambda into W transpose W minus 1, this is what we had, right. That is interesting. So, W is basically a scalar, so I will write this as lambda into W transpose W plus lambda into W transpose W minus lambda, this is what we had, L is equal to, right. Now, what is W transpose W? We were basically looking for that unit vector, therefore, W transpose W is equal to 1. So, which implies we have L is equal to lambda into 1 plus lambda into 1 minus lambda. So, these two will get knocked off. So, what we get? We get L is equal to lambda, right. So, what should be the thing? So, we have to look for the largest, the eigenvector corresponding to the largest eigenvalue. So, to maximize the variance we choose the eigenvector corresponding to the largest eigenvalue. Eigenvalue of the covariance matrix. Right. Okay. So, the goal is basically to find out the direction of the largest the maximum variance which corresponds to the eigenvector of the largest associated with the largest eigenvalue. And if you look at the okay, so what we do is PCA basically says that okay, this also is something based on our matrix calculus and stuff what we have done. We have established that if you want to, I mean you are looking at the direction of maximum variance, it must correspond to the eigenvector associated with the largest eigenvalue of the covariance matrix. Okay, great. So, now what do we do after having done all these things? Our goal is now to obtain that value of the parameters which would actually maximize or minimize our cost function. How are we going to do it? We will look at the idea of gradient descent and stochastic gradient descent, which will be done by Gaurav Hegde in the next lecture. So, in this lecture what we have done, we have basically looked at the least squares and the idea of principal component analysis, where we have established certain things which we studied. Mathematically also we have established this, and in the next class when we come back, Gaurav Hegde will be looking at how do we get to this optimal point, how do we get to that set of x which will give you this optimal which will optimize the function, the cost function, right. That will be done by Gaurav, where he will be talking about gradient descent and stochastic gradient descent. Namaste.